my knowledge, are still produced by this Scotch tape method. But even to obtain this glass phosphor material is not trivial. You have to convert it. Even glass phosphor is one of the most stable form of phosphor. You have white phosphor, red phosphor. White phosphor is for explosives. Red phosphor is for matches. And black phosphor is the most stable form, but you have to form it in a very special environment. So right now, one of the methods to create black phosphor is to mix red phosphor, which is common material, with tin and some tin indium iodine. And then seal it in a glass tube and then heat it up so that the red phosphor will evaporate and carried by this indium gas, and we deposit into a form of glass phosphor. Now, below a temperature of 550 degrees C, glass phosphor is the most stable form. So you will form glass phosphor. And it is this needle-like structures that you see here, and you can confirm their existence from Raman spectroscopy. However, the breakthrough is still required to have some direct synthesis. Otherwise, we would this material will only be limited use in the lab. So, in terms of status, I think the graphene has a much more mature status than the other materials, but we have to take into account that graphene also have a longer history than the other other 2D materials. So we have to give it some time, but the time is catching up because within 5 years, as I mentioned, that graphene was able to make very big leaps in terms of synthesis. Now in electronics, this was a roadmap proposed by one of the Nobel Prize laureate, Novoselov, in 2011, 2012 for graphene. He envisioned that the first industrial application in graphene will not be transistors, but rather in consumer electronics for flexible and also wearable electronics because of this transparent and high electrical conductivity features. So actually, there are indeed products that are made based on these features, and this is not yet realized. But in the long run, in the more future, when the graphene quality continues to improve, that you can have bigger wafers than I've shown you earlier, we can start thinking about the transistors and also the future devices. The first application that came to mind was RF transistors. It comes into a very niche position because, as we know that graphene has a zero bandgap. Zero bandgap means that you cannot really turn off the device. And leakage control is one of the key features for CMOS to scale. So that means graphene device cannot be used in CMOS in future nodes, period, because of the lack of bandgap in this material. However, in RF devices, we don't necessarily have to go into this bandgap regime. So this is a current as a function of gate in a graphene device that shows this, we call it ambipolar device characteristics, that the current can be modulated by the gate from high current to low current and back to high current again. You have this shape because you can have transport due to holes or electrons depending on your Fermi energy. And as I will mention again here, this is the off state, so-called off state. It still have a finite current, actually quite substantial current. So this is we call it very poor on-off ratio, very, very bad for digital switches. But for RF, you don't have to turn off the device. You want a device that can amplify your high frequency signal. You have a very small input signal, but have a much higher input in the end. So this is how it will work. You pick a region where you can, relatively linear region where your input signal could become an output signal with a larger amplitude. And this amplitude will depend on this gain, so-called amplification gain, will depend on the slope here, which is defined in this feature. And this GM is proportional to your mobility. So the higher the mobility, the higher the GM, and the higher the frequency you can operate at. So because of, we can use this simple equation. This is the cutoff frequency. This is the frequency when the current gain becomes 1, and it's proportional to the GM. So in the 2009, we already demonstrated the first graphene transistor on the wafer scale with an operating frequency up to 100 gigahertz. The next will become trivial, just continue to scale, but then we also put this into an integrated circuit, so you can actually have some useful function. You can have a mixing function and then have an output mixing at 4 gigahertz and output at 200 megahertz. By scaling down the gate length, you can increase the frequency beyond 400 gigahertz. So this was the work in 2012. So you can see that once the niche application has been identified and the principle being known, you can make really quick progress in this field with a certain maturity of the material. However, back to the CMOS, the digital switches, where a bandgap is urgently needed. Efforts also have been made to try to create bandgap in graphene using a nanoribbon. The idea is that through quantum confinement, you can create quantum states that create a bandgap. And indeed, with some nanoribbons, you seem to have some kind of bandgap, but you can see a lot of noise, and it's still arguable if what you're seeing is really the result of a bandgap. And the reason to, one of the challenges for this to work is to control the edges, because in a bandgap, you etch graphene into a ribbon-like structure. So you will have some kind of uncontrollability due to the process that causes the edge roughness, as you see here, or the width variation. Now the width variation will be even more dramatic in changing the material from a semiconductor to a metallic. So with some change, just by changing one line of atoms, you can change this property from metal to semiconductor. So it is a very, very challenging task to atomically control the edge in order to create a bandgap in graphene. But I still put it here because I know this is still one of the ways, probably the most obvious way to create a bandgap in graphene. Now in other 2D materials, it becomes relatively easy because it already comes with a graphene and with a decent mobility. So graphene even has a very good mobility, 10,000 to 100,000 of mobility. By the way, silicon is roughly about 200 to 1,000. So this is definitely much, much higher than that of silicon. And glass phosphor and TMD material, they have bandgap, so they have a relatively larger on-off ratio, but they, because of the larger effective mass, the mobility is lower. But I'm showing here is that these three materials, they actually cover a wide range of on-off ratios that you can mix and match. If you have the freedom to pick any material you want, you actually have a pretty good toolbox to select from. But again, the wisdom is how to down select the material. Is that when you have 140 materials to choose from, that becomes a challenge as well. And 2D material, MOSFET based on this 2D materials with a bandgap has been demonstrated. So this is a work that was published this year in the VLSI symposium that shows the MOS2 material with a gate length down to 11 nanometers, but still having a very good on-off ratio and a reasonably good switching slope. We'll talk about more about this slope later, but now just keep in mind that 90 millivolt per decade is a respectable number that shows that the switching is pretty good. And it also actually agrees quite well with the projection that the lambda, the length is still much larger than the five times of the lambda. And glass phosphor has a higher mobility. By the way, this device, even though it has a good on-off ratio, the mobility is in the range of 10 to 20. That's quite low for the perspective of silicon. Glass phosphor has a relatively higher mobility, about 200. The on-off ratio is about 5. So this is all a good starting point for consideration of a CMOS transistor. One issue of the glass phosphor, though, is its stability in air. It actually will start to oxidize and then vaporize in air if you do not passivate it. So this is a piece of graphite with two parts covered by graphene, and this part exposed to air. And you can see within a day you start forming these bubbles, very rough surface on the glass phosphor. So they disintegrate quickly, and you need to come up with some kind of passivation to passivate glass phosphor. But once you passivate, then they become quite stable, and you can make devices that are stable and can be repeatedly measured by measuring by days or even weeks. Another issue that's common in the 2D material is the contacts. Remember that transistors, we have, in the on states, the current will flow through the transistor, but if you have a large contact resistance, then it will become the limiting factor. And the ITRS roadmap, this is the industry projection of what the device characteristics should be in the future, that calls for contact resistance of 0.06 ohm per millimeter, or like 65 ohms per micron. In a graphene, you can get to a value that's quite close, but in other 2D materials, MOS2, Phosphorene, they're still 2 orders magnitude larger than this industrial requirement in 10 years. So a lot of efforts that still have to be made, and there's a lot of studies, but I think it's still a lot of progress that are required. And now I would like to go to a different type of device. So far we have talked about the applications of 2D materials in the so-called MOSFETs. The switching of MOSFETs in more details like this. In the off states, you change using the gate to change the electrical potential in this battery area. So suppose you have 2 potential positions, A and B. This is a Fermi-Dirac distribution of your carriers. The carrier that can go through the barrier is this thermal tail that has the Boltzmann distribution. So the ratio of the A and B current actually is equivalent to this very simple equation that dictates switching behavior that tells you that when you change your voltage by 60 millivolts, you can only change your current by 10 times and not larger because of this thermal tail. So there is a certain slope that's dictated by this mechanism. And if you want to go to a lower voltage operations, you have to eliminate this thermal tail. And one of the ways is using the tunneling behavior. So this is another idea, tunnel FET with an NIP. So instead of N plus in both sides, you have PIN structure. So your band structure will look like this. In the on state, you can enable tunneling from the valence band to the conduction band. And you don't have this thermal tail problem because you can limit your current by the bandage of this conduction band. So in this case, in principle, you can have a much sharper switching, and that enables a low power and low voltage operation. And why is that important? Because when we scale the device, we also want to enable low power operation, so to limit the use of power in a given chip. Remember, we have billions of transistors. Each power matters when you add up. So this is a switching slope. As you can see here, conventional MOSFET has a slope. This is current as a function of gate. They are limited by this 60 millivolt per decade. While tunnel FET could in principle have a much sharper slope. So to reach to same current level, you don't have to operate the gate voltage in such a large range. So you can operate at a smaller voltage window. So that gives you an advantage of lower power. And what kind of features are needed for this tunnel FET to work? It actually requires a very good electrostatic control. So again, the 2D material, the benefit is that the body thickness is atomically thin. So you can enable, by principle, the best electrostatic control you could have on a 2D material. So you could have a doping on the P side and on the source side, and then N-type doping on the drain, source and drain respectively. And with a very good electrostatic control, you can have a operating tunnel FET. 3D materials, in principle, you can also create tunnel FET, but when thin down the tunnel body thickness, you suffer from mobility degradation and also a lot of trap charges. Now, so this was a simulation that was made for a different type of 2D materials. That shows that for certain type, this tungsten telluride, in principle could give you the best arm current and can have a better performance than silicon devices. We'll go to this slide, this chart in more detail later. Now the reason for the tungsten telluride to be better than the MOS2 is actually because of smaller effective mass and also a band gap that's smaller than MOS2 when you use heavier materials. Because in the tunneling behavior, you want the band gap to be small, effective mass to be small to have a higher tunneling probability. And if we put the 2D tunnel FET compare with other 2D tunnel FETs made from silicon or germanium or 3-5s, where do they stand? So this is a simulation from the previous slide. And you can see that this is a swing, substrate swing, the smaller the better. This is the drain current, the larger the better. They actually fit in this void in this chart. So 2D material indeed have certain advantage over 3D materials for tunnel FET operation. And what about blast phosphor? There hasn't been much work done for blast phosphor yet, but from a very simple bank structure considerations, we can judge whether they could be even, if they could be superior to TMD materials. Now, blast phosphor is an anisotropic carrier, so you have a very small effective mass in one direction, large some effective mass in the other direction. So that actually gives you an advantage of small effective mass. And the band gap could become as small as half a volt. So this is also an advantage. So the multi-layer blast phosphor is actually quite promising because you can maintain a direct band gap for any number of layers. You can control the band gap. You can tune the band gap by the number of layers. While in the case of TMD materials, remember that they become indirect band gap when you have more than one layers. That means your tunneling current and probability will start to suffer significantly. And there are also other ways of tunneling. Here I give you an example of vertical tunnel FETs. Then the idea is like this. You have 2D material A and 2D material B. In this case, your tunneling occurs from one material to another. The operating principle is similar, that you tune the band alignment of the two materials so that they can be tunneling when there is a window in energy, overlapping window in energy. And this is one of the preliminary results that was made on MOS2 and tungsten diselenide. One of them is N-type, the other one is P-type. That shows a very pronounced this NDR, negative differential resistance behavior, indicating the tunneling current between the two materials. So this is not yet a tunnel FET, but shows the direction to go to this vertical FET. However, why do we want to use this term vertical FET? The advantage is that you can enhance or increase the overlap area to give you a larger tunneling current that could be competitive to MOSFETs. So this was a benchmark that was made by Intel earlier this year, that they collect all the possible candidates for future CMOS. And they benchmark in terms of the energy versus delay. So that means delay is equivalent to speed. So on this chart, the higher speed is smaller delay in this left corner. And this energy is the switching energy for each switching operation for this 32-bit adder. So the smaller the energy, the better. And the CMOS are these two green dots. Tunnel FETs actually scatter around this area that in some cases they could have a better energy delay product versus silicon. And so that actually shows that the tunnel FETs and combining 2D could be a very promising candidate for future CMOS enabling low power, higher density operations. So here is the conclusion of this presentation, that 2D materials, they have potential for future electronics. The real benefit is because of the thin body. So far, we still haven't been able to demonstrate the full advantage and the potential yet, but we have to take into account of the relatively short history of the TMD and blast phosphor materials. The synthesis will always be the key factor in determining this technology will be useful or not, and the defects in particular. If you can make a very low defect materials with good control, domain size, that would be very desirable. And other fundamental challenges that we have to look into, and still a lot of work needs to be done, are contact resistance, how we dope the materials. We didn't touch this, but this is still a very active topic right now. And also the gate stack options, how you stack high K electrics on the 2D materials that's free of dangling bonds. And finally, I would like to thank you for your attention. I'll take the questions you have. Thank you.
Could you make a quick comment on the vertical device using the 2D material and also the planar device? I think you mentioned some tunneling activity.
Yes.
So the challenge in the technology or some difference in intrinsic property?
Yes, that's a very good question. Actually, this is, even though this looks like a planar device, you can make this in a vertical structure as well. But the idea to make this work is actually to control the spacing here and the clean interface of these two materials. You don't want them to have any covalent bonding, because then you will have a direct current conducting path that destroys your FET operation. So for this kind of device to work, it has certain criteria. It has to be smooth with only van der Waals interaction, and this spacing has to be engineered just right, because this is a tunneling, and we know the tunneling is very critically dependent on tunneling distance. So any variation of the tunneling here will have a big impact in your final curve. And in a planar, you mean the MOS or?
Yeah.
They will probably take up pretty much the same footprint in the device. But how we grow this architecturally?
For this case, you need a spacer. You need a spacer?
Here, in between?
Yes, just 6 angströms actually.
In this case,
actually,
not necessarily. Vacuum will be good.
Okay.
Yeah.
So it will be stable?
I mean, this is the work from this group. At least from their result, they indicate that this was vacuum gap. So that's why you need, this is a van der Waals force interaction. It's not a direct conducting path, but it's actually a vacuum gap.
So I follow this question. So what's the tunneling barrier? So for planar device, the tunneling barrier normally is the bandgap.
Yes.
For this one, what's the tunneling bandgap?
That's related to the band alignment of the material.
So you have a vacuum. You have a vacuum. There's not two material. There's a vacuum in between.
Right.
So the barrier height should be different in the planar. Also, you should look at the papers, chemistry paper. They have different feeling as the physicist.
Yes.
So what's the barrier height in the view of physics, not the chemist?
I'll say right now, the key actually the barrier is actually this is the barrier height. But let me finish. The one more important question is what's the overlap integral? And this is the question that I think no one has the answer, even from theorist point of view, is that the electron orbits here and the electron orbits here, what's their overlap integral? And we also with respect to their lattice orientation, that will have a big impact. And this overlap integral will actually be the more important factor in determining the tunneling current in this fashion. And so right now you can assume certain overlap integral between the two materials and then come up with the current number, but it's very sensitive to this energy of the overlap. So I think that would be the more relevant parameter to look at. And
right.
Bandgap,
From chemist's point of view, if we from the WKB method, right? WKB,
yes.
you need a barrier height to calculate the WKB.
Yes.
So what's the barrier height if you have vacuum in between?
That will be infinite.
Yeah. Yeah. So that's
yeah. Yeah. So that's why I think in this case but we are not talking. I mean, we are talking about electron tunneling, and it's actually more related to your overlap of the wave functions from the top and bottom materials.
Maybe some DFT experts can make a comment for calculation. I think it's already possible to make calculation for the STM. So it's different, even with a different orientation. I think this is also possible. Will be interesting.
Yeah, definitely. I think if we can quantify some of the number here, that would be very useful in determining whether this device could be useful for technology, for future switches.
Okay. Any other?
Is it doable that the graphene be used by double heterojunction for laser application? Double heterojunction.
I probably am not the best person to answer this question. So yeah, I haven't thought about this.
Laser application.
I'm sure there are
Micro laser.
probably people working on that.
People working on the graphene and also 2D materials about the laser and modulators, receivers, so there will be optical interconnect.
Yeah, that.
They depend on a lot of, as Dr. Lee says, materials, the important issue, or the ohmic contact, and so on and so forth.
Yeah, there work in Cambridge University. They did a lot of optical applications based on graphene and so 2D materials. Graphene is a modulator for optical communications, but I'm not the expert in that field to comment. So.
Any other?
Yeah, so thank you for this very nice talk. And I'm curious about how to dope these two-dimensional materials. I understand that you mentioned it last time. I already written a note in my when I hear your talk. I'm very interested about how to dope the material. There was a slide you mentioned is 2D vertical structure is N material,
yes.
P material.
Yeah,
so,
I mean, like this, you need for the FET. Eventually, you have to dope the device, dope the channel. As you probably are aware of very well from the literature, that there are known techniques to dope the material by charge transfer with some physical molecules that either have a higher electron affinity or long electron pairs that could transfer charges to the 2D materials. That has been shown by many groups. For example, you can put in one extreme case for potassium would heavily dope these 2D material into N-type potassium atoms because they like to give away electrons, and then they could physically on the surface of the 2D
So
material.
it's similar to conventional electronic materials that we dope the silicon substrate by bombarding.
No. For 2D materials, it's hard to imagine that scheme would work.
Right.
Yes, because it's such a small thickness,
Exactly.
and you create defect in the lattice as well. So what usually happens is you have these 2D materials. Imagine that you sprinkle sesames on these 2D materials. They would physically stable on the surface, and there are interactions between this molecule and the underlying 2D materials that either donate electrons or holes to the substrate. So it is like remote doping. It is like remote doping. The charge providing center is not in the lattice of the 2D material. It's actually in the vicinity of the material.
So it's also achieved by chemical vapor deposition, similar thing, or?
Yes, it could be done by either vapor deposition of this molecule of your choice, or by say PVD, or in some cases, which is favored by chemists, by dipping in the solution.
Oh, okay.
Yeah.
It's a very short period of time.
Yeah. With a short period of time, you can have some molecules that absorbed on the surface without destroying the lattice. Yeah. So this was the techniques that's been applied and used by many groups to dope the materials. But it's hard to control the doping levels with this method.
Exactly.
So there's still some work that need to be done in order to get a more controllable way of doping. So that's why I think there are proof of principles that you can dope this N-type or P-type, but to be precisely have the precision of the doping, that still work to be done.
So which one would be more advantageous to